Okay, algebra students, we're going to go ahead and talk about graphing quadratics. So chapter 8 is about quadratics, and chapter 7 we did a bunch of factoring, and almost all of our factoring was with quadratics. We had an x squared, we had an x, we had a regular number, also known as a constant. And in chapter 6 we talked about different polynomials, where if there's no x, it's called a constant. If there's just one x, it's called a linear function. And then if there's the highest x exponent is squared, it's now a quadratic. And so we're trying to tie all this stuff in together. So today we're working with quadratics, where our highest exponent for x is squared. The highest exponent was to the third, it'd be a cubic, and to the fourth would be a quartic, and to the fifth would be a quintic. But we're going to work with quadratics. And so what we have here is we actually have a graph that is a quadratic. So here's our quadratic graph. It looks kind of like a U shape, not really a V shape, because our absolute value graphs were V shape. Those were our absolute value graphs. And this quadratic is y equals x squared. It's also known as kind of our parent function. It's the basis for all of our quadratics. Now the equation for every single quadratic function is y equals ax squared plus bx plus c. So these letters a, b, and c are all numbers. Now there's only one caveat, and that is a cannot be 0, because we have to have an x squared for it to be a quadratic function. If we didn't have an x squared, then this would look like y equals bx plus c, which really is our linear function, y equals mx plus b. So thinking about how those are slopes and y-intercepts. So without this, we just end up with that. So to keep it a quadratic, we have to have this ax squared. Now, our graph up here is actually the form y equals 1 x squared, because remember, if there's no number in front, there's really a 1, and then there's no x's and no constants added on. And so here we can identify our a is 1, our b is 0, and our c is 0. And we use that kind of guideline, this quadratic equation guideline, to determine if anything's a quadratic. So when I look at my first problem here, is this a quadratic? Well, no. There is no x squared term. So right now, we could say no, there isn't, because if it doesn't have the x squared, it is no longer quadratic. It is now just linear. So now we can look at the next one, and you know what? Let's get our y by itself. So let's move this to the other side. So now this looks like y equals 10x squared plus 9. And we can even write it as y equals 10x squared plus no x plus 9. And now we have it written in that quadratic form. It's written as a quadratic equation. It fits perfectly. So we can say, yes, it can be written as a quadratic equation. And we just proved that right here. And so all of this is giving us reasoning on why we're answering. We can't just say yes or no, because we may have no idea what it really means. And so we're going to find more and more often that we need to explain why our answer is the way it is. So our work helps with that, and our explanation there does. So on our next one, let's go ahead and move our x over. So now we have y equals 2x squared minus x, and then plus no number at the end. And see, now that's written in that quadratic equation. We've got our x squared, we've got our x, we've got our constant. And so yes, this is a quadratic, because it can be written as a quadratic equation. Okay, and then our next one, looks like we got a lot here. Let's move this over. Not seeing any like terms there. So now we have y equals 2x to the third plus 5x squared, because we write this in the proper order, minus 6. And is this quadratic? Well, there's an x squared, but is this our highest exponent? It isn't. X to the third is our highest exponent. So this isn't quadratic anymore. It is now a cubic. And we've just shown that right there. Okay, so now we've talked about how can we tell by looking at an equation, is it quadratic? We've even in here talked about how do I write it as a quadratic equation. I write it in the proper form, which is going to be helpful later on in this chapter. And now we're going to say, okay, well, what if I have a table? Can I look at a table and tell if it's a quadratic? Can I look at a table and tell if it's a quadratic without graphing it? And so, yeah, we can. And we did this in chapter 3. We looked to see if something was linear. And we could tell if it's linear because every time I looked at my x's, there was a constant change in my x. So here, my change in x was positive 1. And then I looked at my y's, and my change in y was constant. Each time I added 3. So my change in y was plus 3. And in fact, we use this with our linear problem. Oh yeah, it's linear because it has the same change each time. And we use this to find slope, where our slope was how our y's change over how our x's change. And so yeah, this is a line. And in fact, my line is going to have a slope of 3. Well, we do something similar with quadratics. Our x's are still going to have the same constant difference, so each time I'm adding 1. But our y's are not, which gets us to the idea that, you know what, they're not going to have a constant slope, and they're not supposed to have a constant slope, because if it did, it'd graph to be a line. Because it graphs to be a curve, we get this pattern of change occurring. And so that's going to help us graph later. But how do we tell if it's a quadratic just by looking at that? Well, I take this pattern and I look to see if that pattern has a constant difference. And it does, because each time, here I add 1, I add 3, I add 5, I add 7. And from those numbers, they each add 2 to get to the next number. And so this second difference is what it takes to be a quadratic, when they have the same second difference. And so now we can look at any table and do the same thing. Okay, how are my x's changing? They're changing by 1, so we're good here. Now we look at how our y's change. Let's see, I add 7, I add 1, I add 1, I add 6, and then we look here, okay, I minus 6, I add 0, and then I add 6. Those are nowhere near the same. So, nope. Second differences are not equal. So now we're going to go ahead and look at the next one. Okay, let's see. I add 1, I add 1, I add 1, I add 1. We're good here. So now let's see. I minus 3, I minus 1, I add 1, I add 3. It looks good because right now I'm seeing a pattern, which we like to see a pattern. And then here, let's see, I add 2, I add 2, I add 2. Yep. These are all the same. Yes, second differences are the same. And so these patterns are all things we're going to use to help us graph later on. Okay, so how do we graph now? Well, remember how at the beginning we said that it graphs to be that U shape? So it can look like a U shape like this, opens up, a U shape that opens down like that. That shape is called a parabola. And so every time we graph a quadratic equation, we should get a parabola. And what we're going to do is we're going to graph this the way we graph anything we don't know how to graph, and that is with a table of values. So I pick values for my x. I've already picked -1, 0, 1, 2, and 3 for you. And we're going to plug those into x. We're going to find our y, and we're going to graph our points. So now we're going to go ahead and we're going to start with y equals 2, and I'm going to plug in the -1. -1 squared minus 4 times -1 plus 2. And we're going to see what we get. So -1 times -1 is +1. In fact, every time we square a negative number, we're going to get a positive, because negative times negative is positive. So -1 times -1 is +1. 2 times +1 gives me 2. -4 times -1 gives me +4, and then plus 2. So now 2 plus 4 is 6, plus 2 gives me 8, which means my point is going to be -1, 8. And there is 1 point on my graph. And now I have to do this enough so I can see the U shape. So I keep going. Y equals 2 times 0 squared minus 4 times 0. I love the number 0. Because 0 squared is 0, 2 times 0 is 0. Minus 4 times 0, which is 0, plus 2. And that just gives me a number 2. So now we have 0, 2, which graphs right there. Now we plug in y equals 2 times 1 squared minus 4 times 1 plus 2. 1 times 1 is 1. So now we have 2 times 1, which is 2. Minus 4 times 1, which is 4, plus 2. So this gives me -2 plus 2, which is equal to 0. So now I graph the point 1, 0. And then I go on. Y equals 2 times 2 squared minus 4 times 2 plus 2. See, 2 times 2 is 4. 2 times 4 is 8. Minus 4 times 2, which is 8, plus 2. So that gives me 0 plus 2, which is 2. And I'm starting to see that U shape, but I got to keep going and fill out my table. So y equals 2 times 3 squared minus 4 times 3 plus 2. And so this gives me 9. 2 times 9 is 18. Minus 4 times 3, which is minus 12, plus 2. So this gives me 6 plus 2, which is 8. So then we have 3, 8. And there's our parabola shape. And that is a lot of work. And I understand that it's a lot of work. But the nice thing about this is if you know how to do this and you can calculate this stuff accurately, you can graph anything without actually knowing what it's going to look like, which is really cool. We are going to learn the patterns so we don't have to do all this work. So some pattern stuff that I want to show you. See how there's an 8 here and an 8 here? And how that pops up on each side? That's what we call symmetry. There's symmetry of our table and there's symmetry of our graph. Now look here, 2 and 2. Boom. Symmetry to our graph, symmetry to our table. And then we have the number right at the bottom, also known as our vertex, where that line of symmetry goes through to separate our graph into 2 perfectly equal parts. And so we're going to use that idea of the symmetry that happens to help us graph. So we'll practice this in class, and I'll see you next time.